For so for my microfluidic experiment, I wanted to measure the surface tension of water, and I did it using droplets and just making a very simple free body diagram of a droplet. I'm able to do that because I have this dropper, so I will, I can squeeze this dropper and get little droplets coming out. So I'm going to try to hold one in place and talk about the forces that are acting on this one drop. So I have this drop here. I have atmospheric pressure acting on the entire outer surface of this droplet, and the sum of which in the y direction times the areas in the y direction give me the net force pushing this water droplet up. I also have the weight of this water droplet, so I have some mass times gravity pushing it down. At the interface of the droplet with the rest of the water column in here, I have four important forces. So the first two are due to pressure. So I have on it two pressures. The first one is going to be rho g times this height of water. So the density of water times gravity times the height of this column is pushing the water droplet down. I also have the not the atmospheric pressure, but the gas pressure at the top of this surface that gets transferred to the bottom. So I have two pressures. One's rho gh, the other one is this gas pressure that's pushing the water droplet down. And then I have two forces that are pulling it up. I have surface tension times the perimeter is a force that's pushing pulling the water droplet up. And then I also have the water droplet interfacing with the plastic tube, and that's going to create some contact forces. I think plastic is typically charged or polar, so you're going to end up with hydrogen bonding, and you end up with these forces pulling the water droplet up. So those are all the forces acting on that water droplet. I have an FBD here of it. It's backwards because I'm filming it, so I apologize for that. But again, I have all the atmospheric pressure on the outside. The sum of those in the y direction are just going to be A times some area pushing it up. I have the weight pulling it down, and then I have those four forces at the interface. Now this one is the gas force. So I have rho gh times area, and then I have the gas pressure times the area. Now I'm going to do the experiment such that this gas pressure actually ends up being atmospheric pressure. And the reason I need to do that is so I can take this force and I can cancel it with this force. And then obviously all of these guys cancel with all of these guys. So I end up with, if I do the experiment such that this is atmospheric pressure, I can cancel this guy with that guy, and my FBD reduces to this here. So now I'm going to have the weight, I'm going to have surface tension, I'm going to have rho gh times this area, pushing it down, and then I have these contact forces pulling the water droplet up. I can calculate this, I can calculate that, I can calculate this 2 pi r. What I can't calculate is these contact forces. So really what's happening with this water droplet, this is the water column. On either side here I have the plastic tube, and then I have the water droplet. But I get a lip here. And this lip is going to happen, and I'm going to have some contact surface here, and this interface is going to create these contact forces here. I can't calculate these. So I have to make an assumption. And the only good reason to make this assumption is that this rho gh times A is downward, these contact forces are upwards, they're in opposite directions. That means the net of these guys should be smaller than either of them together, alone. So I'm just going to assume that that's negligible, and I'm going to cancel both of them. I don't know how good of an assumption that is. The only reason I know it was reasonable is because I got a decent value for gamma. I do know what I could do to minimize these forces if I really wanted to be more serious about this experiment. I could create a dropper that was very, very wide. And if I created a very wide dropper, my H would get smaller. And if my H got smaller, then this force would get smaller and become negligible. I could also make a very tiny pinhole. That pinhole would reduce the surface area, and so this force would get smaller. And if this force got smaller and this force got smaller, then their difference would be even smaller still, and I could throw them out, and that would be more appropriate. I don't know how appropriate. It would just be more appropriate than it is now. But anyways, making that assumption that the difference between these two is a negligible force, and throwing them out, I end up with this FBD. which is the final FBD that I use to do my calculations. Again, I have surface tension acting on the perimeter of the interface. These are all gamma DLs, the sum of which equal gamma times 2 pi r, or gamma pi times the diameter. And then I have the weight of the droplet. I can sum the forces in the y direction, and I end up with gamma 2 pi r equals mg. I can solve for gamma equals mg over 2 pi r. So this is a very simple equation, simple math, simple physics. The only thing is I need to be able to calculate this mass, and I don't have that. I do know that the mass of this water droplet is going to equal the density of that water droplet times the volume of that water droplet, and times g times 2 pi r. So these are the equivalent equations. Rho v equals m. I need to be able to get v. I know rho. Rho is 1 gram per mil, so I know the density of water. I need to get this volume. This is the part that became tricky, and I'll show you why. So I can get a mil of water and then calculate the average volume per mil. And the way I can do that is by just squeezing this entire mil out, counting how many drops it takes. Say it takes 30 drops, then I have 1 mil per 30 drops times 1 gram per mil gives me however many grams per droplet. The problem when I do that is that this droplet volume is dependent on those forces, because the droplet doesn't actually break until those forces are right at equilibrium, or right past equilibrium, I should say. So the forces acting on the droplet dictate the volume. And if I'm going to do the calculations the way I want to, I can't use this dropper. And the reason I can't use this dropper is because when the second I squeeze this, I'm changing the gas pressure in this column to some value that I don't know. And if I don't know that value, then I can't cancel it with the atmospheric pressure pushing it upwards. So to do that, I need to take this top off, and I need to expose this top to the atmosphere. And now I know what the gas pressure is here. I can cancel it with the gas pressure on the bottom. The thing, though, is if I do that, I'm going to do it quickly. I'm not actually going to count the droplets because it takes a very long time to do it right. But if I do that, I get some residual water on the bottom. So that presented a problem when I tried to do the experiment. But then I realized that this volume of water, if I do...
Patrons, the science lab will be closing in 5 minutes. Once again, the science lab will be closing in 5 minutes.
If I do it the same way every time, then this column of water is always the same size. And the reason that's true is because it's the exact same forces acting on this column of water. I have the volume of the water times rho times g, pulling it down. I have the contact forces pulling it up. And on the bottom, I have a sheet of water across that little pinhole. And that's essentially a net. I have all these water molecules that essentially make a net, and they're carrying the bulk of the weight of this volume of water. That's another way I could probably calculate surface tension. That's probably a more elegant way or a fancier way, but I didn't do it that way. The problem, though, now is that how do I get exactly a mil out of here? Well, the trick was realizing that this column is always the exact same height. Once I do that, I can expose this to the atmosphere. I get my residual water, and then I take this residual water and I put it into an empty cup. Now I can go in here and take in exactly 1 mil of water, take in exactly 1 mil of water, put in exactly 1 mil of water into this cup, and now I have residual volume plus 1 mil of water. I take in all of that water now, and then I can expose it to the atmosphere. And now I can count how many drops. Once I let all this water out, I'm going to get exactly 1 mil plus residual volume. I'm not actually going to do it because it takes a very long time to do it carefully. But I get exactly 1 mil of water come out of here because I'm left with just a residual volume. And I started with residual volume plus a mil. So doing that, I get 24 drops per mil. And I know the forces on every one of those drops. Now I can take the average volume and then multiply that by rho, and then I get the average mass of those droplets, and that ends up being 41.7 micrograms. And then now I can go back to this equation here, and my surface tension is going to equal 41.7 micrograms times 9.8 meters per second times 2 times pi times 0.75 millimeters. And that's just from measuring that little pinhole with a ruler. And again, that introduces new errors and I would need to know the error in my ruler to do that. Things that I can't really calculate. I know that the experiment made I know my assumptions and my errors weren't too off because I ended up with a value of 86.7 dynes per centimeter, which is very close to the true value of 72 dynes per centimeter. So that was my experiment for measuring surface tension. I measured the surface tension of Dr. Pepper. I think I got like 67 dynes per centimeter. I don't know if it makes sense that soda has less tension. I know it's carbonated and it has sugar, which I think might be a surfactant. So I think that makes sense that it had a lower surface tension. But I can measure the surface tension of any liquid with this household method of just using a medicine dropper and very simple math and simple physics. So thanks for listening. Okay, bye.